Hey y'all, welcome back to Engineer with Musa. Today we're going to be talking about calculating the design flexural strength of the reinforced concrete beam section as shown below. So here we're going to be talking about this reinforced concrete beam section, and what we're interested in is the design flexural strength. So when you think of the term design flexural strength, you want to think about this formula here. Phi mn is equal to phi times as times fy times d minus a over 2. This is the formula for finding design flexural strength. Okay, so let's get started. The first thing that we need to determine is our AS value here, the area of steel. The area of steel is simply the area of these steel rebars over here. So if we do that first, we can say AS is equal to 4 times pi r squared, right? And so this 4 comes from the fact that we have 4 of these steel rebars, and then pi r squared is the area of each steel rebar. So if we go ahead further and calculate 4 times pi times the radius, which is it is going to be 0.5 inches quantity squared, and this 0.5 comes from the fact that we have each diameter. So the diameter is equal to the number 8 bar divided by 8, which is equal to 1 inch. And the radius is just going to be 1 over 2. So that's how I got 0.5. Okay. And so this is going to turn out to be AS is 3.81 inches quantity squared. So let's go ahead and box that. Oops. Now what we also need to determine is D. So D is this variable right here, and D is simply the depth from the top of the concrete beam section to where the rebar is, and that is given as 20 inches. So D is equal to 20 inches. Next we need to determine the variable A over here. So this variable A is coming from the concept of Whitney stress block. And in the Whitney stress block, we know that TS is equal to CC. So TS is equal to CC. And this TS is the tension force in the concrete section, and this is the compressive force in the concrete section. So we can equate TS. So here we know that TS is equal to AS times Fy, and we know that CC is equal to 0.85 times F prime C times B times A. And so we can equate this equal to each other. Like so. And what we're interested in is solving for this variable A. So what we're going to do is isolate A. So A is equal to that. And now we know what AS is equal to. It is, as we calculated a second ago, 3.14 inches squared. FY is given. FY, I believe, is 60 KSI. Divided by 0.85 times F prime C, which is 4 KSI. That's also given over here. And then B, which is the width of the concrete section. So if you look over here, B is simply 16 inches. And so A is going to turn out to be 3.46 inches. So let's go ahead and box that. And next we need to determine what phi is. So we're interested in determining this variable here. So phi is the reduction factor, and we can find out what phi is by looking at ES over EC. ES is equal to EC times D minus C over A. And so this is going to equal to 0.003 times D, which we already know is 20 inches, minus C, which can be taken as A divided by 0.85. So C is going to be A, 3.46 inches divided by 0.85. And then A we know is 3.4 inches as well. .46 inches. So this is going to give you 0.012, and this is greater than 0.05. Therefore, we can establish that phi is equal to 0.9. So if this value here is greater than 0.05, and this is the strain in the steel section, in the steel. So the strain of the steel here is greater than the strain in the concrete. Therefore, we can determine phi is equal to 0.9. This is an arbitrary reduction factor. And now we can just go ahead and calculate phi times mn, which is equal to phi. Well, I can just simply copy and paste this formula here. So let me duplicate that, drag it down, and now we can go ahead and plug and chug. So we have 0.9 times AS, which is, as we said over here, 3.8. And then Fy, which is 60 KSI, times D, which is 20 inches, minus A over 2. So A we know is 3.46 all over 2. So phi times mn, which is equal to 258 kip foot. So that is the design flexural capacity of this concrete beam section. Thank you for watching, and I'll see you on the next one.